All right, so good afternoon, honors pre-calculus friends. So it's Sunday afternoon, and I'm going to make a video here about the lesson that we were supposed to do on whatever day it was, Thursday, I guess. So we were working on this pattern right here, so I'm just going to pick up where I left off. Sorry, this is going to be not as interesting as it would be in class because it's just going to be me talking, and, you know, that's just the way it is. Sorry. Okay, so we were in the middle of this pattern right here. And so we had figured out that I to the first, I to the 0 was 1, and I to the first was I, and we already knew that I to the second was -1, and we knew that I cubed was just going to be I squared times I to the first, because we had the exponents. So that's -1 times I, which of course is -I, and then we got I to the fourth is I squared times I squared. Remember adding the exponents, 2 plus 2 is 4. So -1 times -1 is +1, and there we are back where we started. So, so I'm interested in finding out the answer to something like I to the 25th, which I think we were actually working on that in class. And so some of you recommended that, well, you know, that's really I to the fourth to the 6th power, because when we raise a power to a power, we multiply the exponents. That's going to be I to the 24th. We need one more, and so that's going to be I right here. So that's I to the first. And so I to the 4th to the 6th. Well, of course, 1 to the 6th is just 1. So it's going to be 1 times I to the first, which is just I. And I to the first is just I. Okay. So another way to actually do this, a quicker way to do this, is really, well, maybe not necessarily a quicker way, but a way that would be more workable with bigger numbers, is just to figure out how many groups of 4, right, 1, 2, 3, 4, how many groups of 4 are in 25. So as it turns out, we just divide 25 divided by 4, right, because it's a group of 4, and that turns out to be 6 remainder 1. That remainder is just the power that we need in order to raise I to. So I to the first will be I. So the answer to this, of course, as we already just discovered, is just going to be I. So in order to do these problems, all we need to do is take the power of I, divide by 4, 1, 2, 3, 4, and then figure out what the remainder is, and then just do I to that power. So easy enough. So let's do I to the 234. So 234 divided by 4. 423 goes 5 times. 20, subtract 3 and 4 here. 4 goes into 34, not 8 times. That's going to be 32. And that's 2 left over, and all we care about really is the remainder. So what we're really talking about here is I squared, or -1 is going to be our answer. -1 is the answer for this one. So I to the 234 equals -1, right? We're just looking for the remainder after we divide by 4 and raise I to that power, and we're done. Okay, good. So find the impedance of a circuit. And circuits in simple terms without any sort of amplifying device such as a transistor or a cathode ray tube or something like that, is going to have a resistor, a capacitor, which is just 2 plates with some sort of separated by something, either air or some sort of non-conductive material, substance, plastic, something like that, and an inductor, also known as a coil. So we just, you know, wrap some wire around either, again, something, or we wrap it around nothing. Either way, we create a coil. What's interesting about the capacitor, again, if you can imagine this, we've already done this problem, so I'm going to use this space right here. So we know that we have a wire, and we know that electrons are flowing through the wire, and a capacitor, like I said, is just 2 plates with some space in between them. So clearly there's going to be some difficulty with these electrons getting across this little gap right here. And so some of them will get across the gap, some of them won't get across the gap. But what we find interesting is that, based on a cool physics experiment from back in the day, a wave is created in order to get these electrons going across. For those who are interested, it's the slit experiment. when we send electrons or light through a slit right here. It looks like we're sending individual particles, but when it goes through, it ends up appearing as though it's a wave. So that's pretty cool stuff. So in any case, so we have a wave, and we recognize, or again through experimentation, that these waves of electricity, I'm just going to draw a little bit of a sine curve right here, can be sometimes shifted a little bit. Let's say we just shift this whole sine curve over to the left by 90 degrees. That's 90 degrees. I'm getting a little too far into this. So I'm just going to shift this starting point over 90 degrees. So we're right here. And so we have this, and the rest of our curve is down here. And so when we do a little shift like this, it's called a phase shift. And as we just discovered right here, 1, 2, 3, 4, there are 4 of these values of powers of I before we start to repeat. And as it turns out, we have 1, 2, 3, 4 major points of the sine curve, or the cosine curve for that matter, before we start to repeat again. So complex numbers are a very convenient way for us to talk about or represent a sine curve and how much it got shifted, how much it got phased out or over to the right or to the left. So that's why we need complex numbers when we're working with impedances of circuits. Resistor is just creating some resistance to the electrons as they are without creating a gap with a capacitor or a coil, which also creates, if you remember from physical science, I hope, creates a magnetic field. And again, the magnetic field offers some resistance and some phasing to the electrical current. So these two guys act very similarly. As it turns out, a resistor has a real component, or is the real component of the overall resistance of a circuit. An inductor, aka a coil, has a positive component of a complex number, and a capacitor has a negative component of the complex number. So we're going to find the impedance, the total resistance, of a series circuit and a parallel circuit. To save time, we're just going to do the series circuit. Okay, so here's what we have right here. So we have a little bit of electricity right here. We'll do an alternating current, symbolized by this circle with a little sine curve in it. And we have a wire coming out, and we have, let's say, a resistor, which again is just a real part right here. And then let's say we have a little capacitor. And then over here on the other side of this circuit, we have a coil. And then, of course, as we know, all electric circuits need to be closed. So there it is. So we have our circuit right here made up of a resistor, a capacitor, and an inductor. So let's say that the resistor has, let's say, 12 ohms. The unit of measurement of resistance is ohm, the ohm, named after a physicist whose last name was Ohm. And we have a capacitor here, and let's say that the capacitance here is going to be, let's say it'll have a small real part, and then we'll have a imaginary part. So let's do minus, so I don't need to do plus. So let's do minus 8i, and let's have a small real part here, plus let's do 11i. And so we want to find the total resistance of this electrical circuit here. So all we need to do is add up all the real parts. So remember, resistors only have a real part, no imaginary part at all. So 12 and 2 is 14 and 1 is 15. And then we add up all the imaginary parts. So no I here, negative 8i plus 11i is positive 3i. So the impedance, or the resistance, of this particular circuit here is 15 plus 3i. Okay. Sorry, Patrick, no time here for looking at Schrodinger's equation for a particle. So, fundamental theorem of algebra. If f of x is a polynomial of degree n, where n is greater than 0, If it's equal to 0, then we have it just a constant. Then f has, that should be at least, at least 1 0 in the complex number system. Now, hopefully we remember that the complex number system is going to be a plus bi, and it's possible, of course, that b could be 0, so that means that we could have 5 plus 0i, aka just 5. So the complex numbers include all of the real numbers. So if you remember a little diagram that you might have seen back in the day, actually I'm not going to draw a diagram because I have neither time nor space. Anyway, a complex number includes all of the real numbers and imaginary numbers too. So this set of numbers is actually bigger than the real numbers. Not really, they're still infinite, but you get the idea. Okay, so note, the roots may have a multiplicity greater than 1. Note number 2. A more helpful way of thinking of this theorem is that a polynomial of degree n has n solutions, some or all of which are in the complex number system. In fact, all of which are in the complex number system, though either the imaginary or the real parts may be 0. I think even the simpler way of thinking about all of this is a polynomial of n degree has n roots in the complex number system. So that's the key idea right there. So a polynomial, sorry for the earthquake here, a polynomial of degree n has n roots in the complex number system. Okay. So when we talk about a quadratic equation, we know that there are going to be two roots. They might both be real. They might both be complex. If we have a cubic equation, maybe we have one real, and in fact we must have one real, and actually we could have 3 real, or 1 real and 2 complex. If we have a 5th degree equation, let's say n equals 5, we have lots of different possibilities here. We could have 5 reals, or we could have 3 reals and 2 imaginaries. And we remember, hopefully, that the imaginary numbers must come in conjugate pairs. So if we got 1 imaginary, we definitely have 2. And so we could have 3 reals. Or we could have 1 real and 4 imaginary. So when the degree is 5, we're either going to have 5 reals, 3 reals, and 2 imaginaries, or 1 real and 4 imaginaries. So the key idea here is we're going to have n roots. Okay, so rational root theorem. If, that's if, right? It may not, but if it does, if a polynomial with q as its leading coefficient, x to the n power, that's the degree, plus a x to the n minus 1, that's the next degree down, or the next power down, plus ... until we get to p, which is our constant term. So if a polynomial of degree n, leading coefficient q, constant term p, has any rational roots, then those roots will be in the form p over q. Again, if it has any at all. So here's what I want you to do here. I want you to list all of the possible rational roots for this. Remember, rational are numbers that can be expressed as fractions. That, of course, does not include square roots of non-perfect squares like the square root of 2 or square root of 3. Doesn't include pi. Doesn't include that special number e that you learned about when you talked about exponential functions last year in Algebra 2. So we're looking for the rational roots, whole numbers, integers, fractions, any of those. So, like I said, it's going to be p over q. So we take all the factors of p, which is our final term here, our constant term. So that's going to be plus or minus 1, plus or minus 3, plus or minus 9. Those are all of the factors of 9. And then we take all the factors of 4, which is plus or minus 1, plus or minus 2, plus or minus 4. And then what we're going to do is we're just going to make fractions out of all of these numbers right here. So we're going to have plus or minus 1 over 1. So that's going to be plus or minus 1. Plus or minus 1 over 2. Plus or minus 1/2. plus or minus 1 over 4. That's plus or minus 1/4. And then we do the same thing all over again. Plus or minus 3 over 1. That's plus or minus 3. Plus or minus 3 over 2. Plus or minus 3 over 4. And lastly, we have 9 over 1. 9 over 2. And 9 over 4. So if this polynomial has any rational roots at all, it's going to be any one of these 2, 4, 6, 8, 10, 12, 14, 16, 18 roots right here. And we could check each and every one of these using synthetic division, right? We could plug in positive 1. We put 1 in the box, run it through this, check to see if there's a 0 remainder. If there's a 0 remainder, then 1 is one of the roots. And we would just keep doing that until we found all the roots. Actually, we would find one of the roots and then we'd divide it down and then we'd use the quadratic and we'd solve the quadratic formula or factor. But anyway, all we're doing is we're listing all the possible rational roots. Back in my day, before Desmos and graphing calculators and so on and so forth, this is what we had to do. We had to make this whole list of possible roots, try them all, or at least try them until we found them. And we might try all of these and then realize, there weren't any rational roots for this thing here at all, which was definitely unfortunate, but just that's the way it was. We also had to walk uphill in the snow both ways. It was terrible. Okay, number 10, complex roots. Complex roots always occur in conjugate pairs, just like the irrational roots. So if 4 minus 5i is a root, then what other root must also exist? Well, 4 plus 5i. I think we already had that in class last time, but just making sure we have it. Right there, 4 plus 5i. Always in conjugate pairs. Okay. Write the polynomial whose roots are this, 3, negative 4, and 3 minus 2i. Well, we just learned seconds ago that if 3 minus 2i is one of the roots, well, then I can assure you that 3 plus 2i is another root. So we're going to do our little quadratic tricks here. So we do our, since this is two roots, we have x squared, right? That's what our fundamental theorem of algebra says. If we got a degree of 2, in other words, we have two roots, then we got a quadratic thing. Add the two roots together. 3 plus negative 4 is negative 1. Flip the sign, and we get plus x. We've done all this before. 3 times negative 4 is negative 12. So that part's easy. And then we do the same thing over here with these two guys. And I think I'm going to turn this into red just because I can. Put my little bracket over there. And so we're going to multiply, and we're going to get x squared, of course. We're going to add these two guys together. The imaginary parts disappear. 3 plus 3 is 6. Flip it, negative 6x. And then lastly, we're going to multiply these two guys together. So square the first, square the second, add them together. So that's going to be plus 13. All right, just a little bit of trickery right there. And just to verify, 3 times 3 is 9. We did that work right over here. 9. 3 times 2i is 6i. 3 times negative 2i is negative 6i, and then we got negative 2i times positive 2i is negative 4i squared. I squared is negative 1, times the negative 4 is positive 4, plus the 9 makes it 13, just like we said. And back to multiplying all this stuff together. So x squared times x squared is x to the 4th. X squared times negative 6x is negative 6x cubed. And x squared times 13, well, that's 13x squared. And x times x squared is x cubed minus 6x squared plus 13x and negative 12x squared. I just multiply the negative 12 by all these guys, plus 72x. And, crap, I should have multiplied this at a time. That's 130, and 26 is negative 156. There we go. So, remember, we're supposed to write the polynomial, so we're going to write f of x equals x to the 4th minus 5x cubed. Negative 18 and 13 is negative 5x squared. 13 and 72 is 85x. And minus 156. And we are done. And that is all I have to say about that. Okay. So, cubed? Yeah, okay, good. So it says here, factor each two to linear and irreducible quadratic factors. So irreducible means unfactorable quadratic factors. One real zero has been given. So we'll do the easier of these two problems first. We'll do this -5 thing right here. So I gave you one of the zeros. And so remember, if x minus 5 is the 0, then, if -5 is the 0, then x plus 5 was the factor that it came from. So what we're really going to do is, because what are we doing here? We're factoring. So remember, factors are things that multiply together. So we're actually going to divide x plus 5 into this thing right here. But dividing x plus 5 into this is really putting -5 into the synthetic algorithm and doing the work. So we got 3, 19, 21, and 5. And hopefully we're going to get a 0 right here. So 3, -15, 4, -20, 1, -5, 0. Awesome. So that means we now have, remember, this is the constant, the x, and the x squared term. So we have 3x squared plus 4x plus 1. And we're trying to factor, so we're going to factor this guy right here. And so this turns out, yeah, that should be good, 3x. And you could factor this with the master product rule, but I'm going to encourage you to recognize that 3x squared is really 3x times x, and there is no other alternative for that, because 3 is prime. And 1 is also prime, and the only way to get 1 by multiplication is 1 times 1, using whole numbers anyway, or integers. And so now we just need to figure out which of these may be plus and minus, but since all of these things are positive, we just turn these into both positives. And then our other factor, of course, was x plus 5. So that is the complete factoring of that thing above right there. So take the root, plug it into the synthetic division thing, if that's practical. We're going to take a look at this problem over here in just a moment, and we're going to find out that it's probably not practical to do it the other way. And then just get all your factors by factoring at the end. Okay, a little bit of a problem right here, -5/3. -5/3 is a fraction. Some of you may or may not enjoy the whole fraction multiplication thing. So it may be just as easy to turn this actually back into a factor. And so that's going to be 3x plus 5. That's our factor. And then just do long division with this guy right here. So put 3x plus 5 out here. And put this in here, and then just do the division. And we will end up with our other bit up here, which will also be quadratic. And then we factor the quadratic if it is indeed factorable. Saving some time, not doing it. Okay. So here we have a 4th degree thing. We have 3 plus root 42. We know, again, that we're going to end up with a conjugate pair for this one. If there is a 3 plus root 42 as a root, then we know that there's going to be a 3 minus root 42. And if we got these two guys right here, we can always turn them into a quadratic in our usual and customary way. So, since this is a quadratic, we know we're going to have x squared. We're going to add these two guys together. Again, the root pieces fall off, and 3 plus 3 is 6. Flip it, and we got -6x. And then we remember that we're going to square this number and subtract that number. So 9 minus 42 is -33. So we're going to divide x squared minus 6x minus 33 into this guy right here, using, again, long division. And when you divide a quadratic into a quartic, we're going to end up with another quadratic. Once you get that other quadratic, you're either going to factor it, well, you're going to try to factor it. If it's factorable, you'll have the factors. If it's not factorable, then you leave it as it's as is. In other words, just leave the quadratic as is. Don't factor it if it's not factorable, obviously. So, again, saving time. Not going to do that. I know that you can handle it. Jumping over the page right here. And good. Getting close to done. Okay. I am, however, going to do this one right here with the complex numbers. Just because. So we have 3 plus 2i, and we got 3 minus 2i. We know that's a guarantee. And again, we're going to do our little quadratic fun right here. So we got x squared. 3 and 3 is 6. Flip it. I don't know why all these are coming out to be 6, but whatever they are. And then that's 6x. And then we're going to multiply these two guys together using the shortcut. Square that number, 3. Square that number, 4. Add them together, plus 13. I feel like that one came up last time. anyway, there it is, x squared minus 6x plus 13. We're going to divide that into x squared plus 6x, I said, plus 6x minus 13. We're going to divide that into that thing right there. 3x to the fourth minus 17x cubed plus 23x squared plus 73x. Damn it. Sorry. Minus 130. 130. We'll just do the best we can. Okay, so x squared, what do we got to multiply that by in order to get to 3x to the fourth? I'm just going to shift everything over here to the left 1 unit, right? Just because I ran out of space over here, so I'm going to crash into that. So I'm going to write the answer over here. It doesn't really matter. So x squared times 3x squared. Ordinarily, we would put that over the x squared term, but right now we're going to put it over the x cubed term because we need some space. So we're going to multiply this by this, and we're going to get 3x to the fourth. Keep distributing. 3x squared times 6x is 18x cubed. And 3x squared times negative 13 is negative 39x squared. And we're going to subtract. And that's nothing. Negative 17 minus 18 is negative 35x cubed. And we're subtracting here, which merely means we're going to add. So we're going to get 62x squared. I got to confess right now, I'm getting a little uncomfortable with these numbers. It isn't feeling right, but we'll give it a whirl. Hopefully it goes okay. And so x squared times what makes negative 35x cubed? You guessed it, negative 35x. So I'll multiply that over here. So we get negative 35x cubed. 35, 180, and 30 is 210. Mother of God. Negative 210x squared. Gee, I sure hope this works out. 35 times 13 is 350, and 105 is 405. Crap, hold on. 350, what did I say? 10 times 35 is 350. 3 times 35 is 105, so that's 455. Getting a little nervous here. That's 73x. Well, yeah, we'll see. We'll see. So we're subtracting here, we get nothing. And this is going to be 272x squared. 272x squared. And we're subtracting, Christ, minus 382, right? 382, 73, yeah, that looks good. Minus 130, really, this is going to come out to be 0? I don't think so. Okay, and, oh, mother of God, that's not going to work. All right, something horrible happened here. 3x minus 17x cubed plus 23x squared plus 73x minus 130 x squared minus 6x. 9 and 4 is 13. There's no doubt about that. 3x squared. 3x to the fourth plus 18x cubed. 30 minus 39, yeah. All right, well, I don't want us to take a whole lot of time here. I'm not sure where my error is, but there must be some error here somewhere. I didn't create this problem, I don't think. I think Desmos created, not Desmos, CUDA created it, so it should be good. Nothing. 272. That's not going to come out to remainder of 0. There's no way. Okay, anyway, so again, somewhere in here there's an error, I guess. And so this, theoretically, after I write some gibberish down here, we should get a 0 for a remainder, and then we would factor this thing up here, whatever this thing was. So again, my apologies for not finding my error in here. Like I said, it's in here somewhere. I just don't know where it is. Because like I said, I didn't generate this problem. It's generated by a nice little computer program, so it should come out okay. But like I said, I made a mistake. But you get the idea. You know, make this into a quadratic. Do our little quadratic trick. Divide using long division. Get a quadratic up here, and then factor this guy if you can. And if you can't, then our factors are x squared minus 6x plus 13 times whatever that thing is, 3x squared minus 35x plus whatever, 17, whatever. Okay, find all the zeros, and I give you 1, 0. So we're actually going to do something very similar to what we just did just a little while ago. So here is one of the zeros, and again, that turns out that we have x plus 5 as a factor. But since we know that x plus 5 is a factor, we can always just do little synthetic division tricks. So we get 3, 16, 3, and negative 10. And we're going to bring this down here. 3, negative 15, 1, negative 5, negative 2, 10, 0. Thank God that worked out okay. So now we have 3x squared plus x minus 2. And we're finding all the zeros, so we're going to set this equal to 0. This has nothing to do with this 0 here, except for the fact that 0 remainder means that that went in evenly. That was a factor. That's a root. And this is another factor right here. So we're going to factor this guy right here. And again, because that's prime and that's prime, we can do the easy factoring here, not use the master product rule. 3x times x is 3x squared. That's the only way to do it. And then 2 is 1 times 2. We just need to figure out where they go. Well, 3 times 2 is going to get us 6, and that's pretty far away from that. So I'm going to put the 2 over here and the 1 over here. And I have a positive x, so I'm going to give us a positive 1 here, because that'll give us a positive 3x. And that'll be a minus a 2x. And so now I see that my solutions, right, we're finding all the zeros, aka the solutions. One of the solutions is here, negative 5. Another solution is here, 2/3. Another solution is here, negative 1. So I'm just going to bring down the negative 5. And there are all the solutions to that cubic equation. Those 3 right there. Okay. Same trick right here. It's the exact same problem. Negative 2, we just put negative 2 in the box. Boom, 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 do all the work. Okay. Okay, yeah. So let's do this one right here. So we got 2x to the 4th, blah, 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 quartic equation. And again, as always, when we have negative 4 plus 7i, we know that we're going to have negative 4 minus, that's root 7, by the way, minus root 7. So we're going to turn this into a quadratic and do our little division tricks. So we got x squared, negative 4 and negative 4 is negative 8. Flip it, make it positive 8. And then we square and minus. So 16 minus 7 is 9. That's our little shortcut for getting through that. So now we're going to divide that into that. And God, I hope that goes in evenly. 9, 90. It's encouraging looking. So we got x squared plus 8x plus 9. Divide that in here. 2x to the 4th plus 15x cubed minus 89x minus 90. Just barely fits. All right, x squared. And we need a 2x squared. Where's that going to go? That's a cube there. That's a squared there. So x squared times 2x squared. So we got 2x to the 4th plus 16x cubed plus 18x squared. And we do some subtracting. Nothing. 15 minus 16 is negative x cubed. And, oh, mother of God. Negative 89, subtract that is negative 99, negative 107. Jesus, this can't work right. Where's my x? Did I lose an x? 4, 3, Jesus. I forgot the 2. Right, there's an x squared in there. I forgot it. It should be here. Yeah, crap. All right. Okay, here's what I'm going to do. I'm going to put this on a separate sheet of paper. And we're going to do it properly here. So we're going to do x squared plus 8x plus 9. Hopefully all of you saw that before I did. 2x to the 4th. I know some of you would have been saying, hey, 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 you forgot your 0x squared. 15x cubed plus 0x squared minus 89x minus 90. Okay, so long division. So we're going to get 2x squared, goes right there. And so we're going to get 2x to the fourth plus 16x cubed plus 18x squared. And we're subtracting, we have nothing, and negative x cubed, negative 18x squared, minus 89x. And we know we need a minus x. And, boy, this does not look good. All right, so negative x times that is negative x cubed. A bad feeling about the last one, it didn't work out well either. Negative 8x squared, and negative 9x. Oh, that looks a little bit better, I think, maybe. Okay, so subtracting those are out. And negative 18 minus negative 8, so that's plus 8. So that's going to be negative 10x squared, and that's looking a little bit better. And this is going to be minus 80x minus 90. Please, dear God, make this work. Yes. And so we're going to have negative 10 minus 10 here. And that's going to be negative 10x squared minus 80x minus 90. And boom, 0 remainder. That means that was a factor, and so is that. And 2, that's negative 20, 5, and 4. Yeah, this is good. So we're going to factor this guy right here to get our solutions, because that's what we're trying to do here, right? We're finding all the zeros. And so we know 2 of them, 1, 2, and we're now going to find 3, 4. So we got 2x, nope, yeah, 2x and x, doing our little special factoring here, right? And then we got negative 10, so 10 here, and nope, it's going to be 5 and 4, right? 10, 8, no, damn it. All right, go the long way. Negative 20x squared, and what 2 numbers multiply to make, so that's going to be negative 5x and 4x. Should have been able to do this in my head, but I'm starting to feel a little time pressured. So we're going to write 2x squared minus 5x plus 4x. So remember, what I was trying to do here is I was trying to factor this without using the master product rule. That's that thing I was trying to factor. But I was having an epic fail. Okay, so what can we factor out of here? Just an x. So that's going to be 2x minus 5. Factor out a 2 times 2x minus 5. And then I have x plus 2 times 2x minus 5. And we have negative 2. And we have positive 5 halves. And then we have these answers up here. Negative 4 plus root 7. Negative 4 plus root 7. And negative 4 minus root 7. Those are the solutions from that problem. Okay. So now back to the page at hand. So we're finding all the zeros. In this case, we're going to find all the zeros, and I gave you one of them. This time, I'm not giving you any of the zeros. But fortunately for us, we have learned that after you graph something, you can find the zeros. All you need to do is look at where the graph hits the x-axis, and you will have your zeros. So what we need to do then is graph in your graphing calculators 5x cubed minus 9x squared plus 3x plus 1, and very conveniently the graph of that is right here. 5x cubed minus 9x squared plus 3x plus 1. I graph this, and I find out that we have a nice 0. So we're looking here for nice, easy to work with zeros. Numbers that are whole numbers, or integers, for example, or maybe a nice, easy fraction to work with, like a half or 2/3 or something. Easy, obvious numbers and zeros to work with, because oftentimes the numbers that are not easy to work with are irrational, like square root of 2 or 5 root 17 or something like that. But in this case, we have x equals 1 is our root, and in fact, we see that it's going to be a double root because it bounces right off the x-axis there. So it's a x equals 1 with a multiplicity of 2. Anyway, 1 is one of our solutions. This did not turn out to be a very nice solution, so x equals 1 was our solution. So once we have x equals 1, we're going to do the same tricks we just did just a moment ago. So remember, we got x equals 1 from our graph, which is really starting right here where we just started, right? Find all the zeros. 1 0 has been given. it was negative 5. I gave it to you. Here I'm not giving it to you, but you're going to find it using graphing, x equals 1. So since that's the root, what do? We put that in our little box right here. And we get 5, negative 9, 3, 1. And then we just do our little division thing right here. 5, negative 4, negative 4, negative 1, negative 1, 0. Thank God that came out to be 0 because that means that's a solution and x minus 1 is a factor. And this thing here is also going to be a factor. 5x squared minus 4x minus 1. We set that equal to 0, and we solve it either by factoring, using the master product rule perhaps, or maybe the little shortcut that I've been showing you. Or we plug this into the quadratic formula and we get a nice answer from the quadratic formula. Same trick holds here for number 21. I'm just going to show you the graph for this so that we can get a sense of this. So here we have, well, this red bit is from the other graph right here. It went up a little higher than I anticipated. So here we have 1, 2, 3 roots. It's a cubic, so of course it has 3 roots. In this case, it has 3 real roots. And the only one that looks nice is x equals negative 3 halves. And of course, on your graphing calculator, you'll see negative 1.5. So, but you know that that's really negative 3 halves, and you know then that the factor for this is going to be 2x plus 3. That's going to be your factor. So I'm going to encourage you to use 2x plus 3 and the whole division thing to get to another one of your factors, which we can use to find the solution. So let's jump back to right here. So we found out that 2x plus 3 was a factor for this because we knew that x equals negative 3 halves was a solution. So we're going to divide, because I said this whole fraction thing can be a little bit tricky sometimes, we're going to divide 2x plus 3 into here using long division, and I hope that my long division works better this time than it did last time. So we got 2x cubed plus 7x squared minus 8x minus 21. And we got x squared right here. That's a good sign. So 2x cubed plus 3x squared, dual subtracting. And we get 4x squared minus 8x. And we need a 2x here plus 2x. A little bit of extra crap on my pen there. Bring that down. Yep, and then we multiply. Right, is that where I'm at? Yep, 2x times that is 4x squared plus 6x, and we subtract. Oh, this is not looking good again, damn it. And we get negative 14x, negative 21. Oh, yeah, good. Minus 7. And that's going to be negative 14x minus 21. Thank God that came out to be 0 again. And here we have x squared plus 2x minus 7. Now, as we look at this, we realize, hey, that's not factorable because there are not two numbers that multiply to make 7 and add to make 2. So since it ain't factorable, we got a quadratic formula it. Let's do the quadratic formula right in this little bit of space right here. Put the quadratic formula right here. So, where are we here? We got 1, 2, negative 7. 1, 2, negative 7, just for me to keep track of what's going on here. So just plug in the numbers into the quadratic formula. We have 4 minus 4 times a times c. Right, we're all doing this nice square root bit right here. Over 2 times 1, which of course is just 2. So we get negative 2 plus or minus the square root of 4 plus 28 is 32. Over 2, and then we have negative 2 plus or minus 4 root 2, because 16 times 2 is 32, square root of 16 is 4, over 2. And then we divide 2 into everybody right here. But we don't divide into the 2 right here, and here's my little analogy for that. Let's say that you order 2 Big Macs and 4 orders of French fries. And you say, no, that order's too big, cut that order in half. So when they cut the order in half, you're going to get 1 Big Mac, 2 orders of French fries, but not 2 orders of cut the French fries in half, 2 orders of half French fries. You're just going to get 2 orders of fries, right? So when you divide by 2 here, you don't cut the French fries in half. So leave the root 2 as it is. Don't turn it into a root 1. right? Just 2 into there, 2 into there. So we get negative 1 plus or minus 2 root 2, as well as the other solution that we came up with before, which was negative 3/2. Same approach as we had above. Okay, those are your 3 solutions. So, and that leaves us with number 22 here, which we would do in the exact same way. We would graph this, and then we would find whatever solutions we can. And as it turns out, the graph to that looks like this. I forgot to make enough space to get to 8 up here. But it has only one nice looking root here. In fact, it has only one real root at all. And this one is negative 0.667. So now you're going to have to use a little bit of intuition to recognize, hey, wait a second. That's just, I use Desmos, by the way. So that's just Desmos not realizing that this is really just 2/3. So this is not negative 0.667, but negative 0.6 repeating, which is really negative 2/3. And when we turn that into a factor, so we can do some dividing, that's going to be 3x plus 2. That's going to be the factor you're going to use to divide into that. Don't forget all your 0 pieces. Okay, so that is all the work that we needed to do on this stuff right here. Your assignment is to do all of these problems. I already handed this out, by the way. So to do all of these problems right here that we haven't yet done, right? I did many of them for you. For example, didn't do number 17, so you're going to do number 17, you're going to do number 19, and so on and so forth. So everything I didn't do, that's what your mission is for your assignment. I think, I'm not 100% certain, but I think I have a dentist appointment, I'm sorry, on Tuesday during your class, so I won't be there, so that means I'm going to have to make another one of these videos. So there it is. Sorry, 46 minutes, but it could have been worse. It could have been 2 hours. So in any case, hopefully you're going to enjoy the Super Bowl. I know that I will be enjoying the Super Bowl and doing a little bit of schoolwork, and I will see, well, I'll see some of you Tuesday, but not necessarily in class. And yeah, that's it. So enjoy the Super Bowl, like I said, and I will see you all pretty soon. Thanks.